Hi guys, happy Friday. Today we're going to be talking about electronegativity and polarity. Don't mind the weird crunching, slurping sounds. That is my dogs chewing on a rawhide treat that I gave them so that they would stop climbing on me. It's working so far, so that's good. Thank you guys for all the feedback that you gave me. It was good to hear from you. And I'll be doing a little video to answer some of the questions that you asked me, hopefully later today, and if not, definitely tomorrow. We will continue to figure this out together, and I'm just going to be kind of slowing the pace down a little bit because that's the kind of the primary thing that I heard from you. So with that, we will start talking about electronegativity and polarity. So the first thing that I'd like you guys to do is take a peek at your student response sheet and answer the following questions about polarity to the best of your ability. I know that we only had a little bit of information on it, perhaps in the bonding notes and also in that bonding POGL that we did. That was kind of hard. Sorry about that. But answer these to the best of your ability. So, why is the hydrogen side of this molecule slightly positive? Why does the head of the arrow point towards fluorine? And that's it. So pause this video, answer these to the best of your ability, and then if you want to supplement your answer, you can. So basically what's happening is that because the nucleus of fluorine is stronger because it has 9 positive protons, it's stronger than the nucleus of hydrogen, which only has 1 positive proton. The fluorine is better at attracting the electrons. So fluorine and hydrogen are sharing 2 electrons in this image, but they're not sharing equally. The fluorine can attract a little bit more of the electron cloud to itself, and because it attracts a little bit more of the negative electrons, it becomes a little bit negative on the fluorine side, and then the hydrogen side gets to be a little bit positive. So the hydrogen side is a little positive because fluorine is pulling the electrons closer to itself and away from the hydrogen, and the arrow points towards the fluorine because the fluorine is the end that's a little bit negative. Okay, so again, on your student response sheet, look at this image and answer the questions. Why is the charge of the nucleus always positive? Why does the nuclear charge attract electrons to the nucleus? And do you think that all electrons are attracted with the same strength? Why or why not? So when we think about our nucleus, if we look at our little picture down here, we have red neutrons and blue protons, and the protons have a little plus sign, and there's nothing on the neutrons. This is because the protons are positive and the neutrons are neutral, and since you only have positive and neutral things, the nucleus is always positive. The nuclear charge attracts electrons to the nucleus because the nucleus is positively charged and electrons are negatively charged, and they're just attracted like magnets because they have those opposite charges. Do you think all electrons are attracted with the same strength? So this is comparing like maybe the inside electrons to the outside electrons, and the inside electrons are much more strongly attracted because they're closer to the nucleus. The outside electrons, like the valence electrons, are not attracted as strongly because they're farther away and there's all the other layers in the way. And so it's harder for the nucleus to attract the far away electrons, especially because there's a bunch of junk in between the nucleus and the outside electrons. And by junk, I mean other electrons. Oh, twice. Interesting. Okay, so this is going to help us to kind of visualize this a little bit better, hopefully. So subatomic interactions, the nuclear charge is the charge of the nucleus. So that's always positive. Here's our nucleus with our positive charge and neutral neutrons. And the nuclear charge attracts electrons in their orbitals to the nucleus. So all these orbitals that you can see on this antimony are all being drawn in towards the nucleus, but they're moving at a high speed, so they don't get sucked all the way in. Kind of like how we're rotating around the sun and the sun's attracting us, but we're moving fast, and so we don't get sucked into the sun. It's not exactly the same phenomenon, but it's kind of similar. So if you have a stronger magnet in the middle, you're going to be better at pulling electrons in towards yourself. So then the other thing that affects your ability to attract electrons is what we call the shielding effect. Shielding effect says that electrons closest to the nucleus block the nuclear charge from attracting the valence electrons. So if we look at these different examples, we have boron, silicon, and antimony. So a little bitty boron has a charge of 5 in the nucleus. It has 5 protons. And then it has only 2 electron rings. So it only has 1 ring between its magnet and the electrons. So boron is good at attracting electrons because of that. And we have silicon. Silicon has 3 rings. So it has 2 rings between its nucleus, which is positive 14, and its outside ring. So those 2 rings block the magnet from the outside rings, and so it makes it harder for this nucleus to attract electrons. Then we look back at antimony. This has all kinds of rings. 1, 2, 3, 4, 5 rings. This 5th outside ring is really far away from the nucleus. And even though the magnet has a plus charge of 51, you can kind of think as every single electron in between that's blocking is subtracting 1 away from the magnet. So it's like this first ring drops the magnet strength to 49, and the second ring drops the magnet strength to 41. I can do subtraction, right? So every time you add a ring, you're like making the magnet weaker, essentially. So silicon and boron, they're like, we don't have a ton of rings between our nucleus and our valence electrons, so we can pull them in pretty close. Antimony is over here like, holy moly, I got all these layers in the way. It's kind of hard for me to attract my electrons, okay? And so atoms with the same number of energy levels are in the same row on the periodic table, and so they have the same shielding effect, right? If you look back at your Lewis dot Pogel, they had all those Bohr models drawn, and you could see if you go across the row, there were the same number of circles, and that's because they have the same number of energy levels. So they're going to have the same shielding effect. But if you go down a row, you added another layer, another energy level, and so the shielding effect isn't as strong. All right, student response sheet time. Which atoms' valence electrons, beryllium, boron, silicon, or antimony, experience the most shielding? So here's your images. And then why do they experience the most shielding? And then which atom's nucleus, beryllium or boron, can attract its valence electrons the most? And which atom's nucleus, silicon or antimony, can attract its valence electrons the least? So that's it. Take a minute, answer to the best of your ability. You're just trying to make an educated guess. And then I'm going to talk to you about the answer. So, the most shielding is experienced by antimony because it has the most layers in the way. If we're comparing beryllium and boron for number 2, which one can attract its valence electrons the most? Well, they have the same number of rings in the way. They both only have one ring in the way. So I'm going to say that boron, because it has this +5, is better at attracting its electrons because it has an extra magnet. So its valence electrons see this +5 with one ring in the way, and the beryllium valence electrons see +4 with one ring in the way. So +5 is going to be stronger because there's only one ring in the way. If we look at silicon and antimony though, silicon has a magnet of 14 positive, and it has 2 layers between itself and its outside electrons. Antimony has a really strong magnet, 51, but it has 1, 2, 3, 4 layers between the nucleus and the valence. And that means that antimony can attract its valence electrons the least, because even though the magnet is stronger, the magnet gets canceled out by all these rows and rows of electrons between the magnet and the outside valence electrons. So hopefully that makes a little bit of sense to y'all, because that's what we're going to be using to study electronegativity, as we're going to be thinking about how strong is the magnet and how many layers are in the way. So electronegativity is the tendency of an atom to attract electrons to itself when it's bonded to another atom. So I really like this cute little picture, not just because it's cute, but because it really shows very clearly how electronegativity affects a bond. So if we have some little atom that is A, and that's purple, and it's really weak, it has a weak magnet, and it's bonded to atom B, which is a very strong magnet, and these little red dots are the electrons. This is a big difference in electronegativity, so they're not sharing equally. So right now, this would be a covalent bond on the top. They're not sharing equally, and atom B is a little bit negative, and atom A is a little bit positive. For an ionic bond, basically what would happen is atom B would just win the tug of war. It would take the 2 electrons. It would have a -2 charge. The purple guy would have a positive charge, and the electrons are being transferred. So a really big difference in electronegativity results in ionic bonding. And that's why we care about electronegativity, because we want to know, is a bond polar, or is it ionic, or is it just covalent, regular covalent? That allows us to make a lot of predictions about the chemistry of what's going to happen. So let's take a moment to think about how polarity and electronegativity are related. Student response sheet. What is the smallest number you see on this table? You've seen this table before in that pogo that we did. So which element is that? What is the biggest number? And what element is that? And describe 2 trends that you see in this table. So the tiniest number that I see is 0.7, and that's francium. And then the biggest number is 4.0, and that's fluorine. So if I'm looking for some trends, I'm going to say, well, gosh, the tiniest number is in the bottom left, the biggest number is in the top right. As you go down a row, your electronegativity gets lower and lower and lower. As you go across a row, your electronegativity gets stronger. So from left to right, electronegativity gets stronger. From top to bottom, electronegativity gets weaker. We are almost out of time for this video, so I'm going to go ahead and stop right here. This will be part 1, and then I will record part 2. Thanks, you guys.